Okay, so today we're going to start with an introduction to sampling distributions. So someone said earlier, they're like, we've already done distributions. Yes, like the rest of this unit is all about distributions, but they're all different, okay? So today we're going to talk about sampling distributions. So until now, a sample mean was just a statistic, which don't forget, like a statistic is a descriptor of a sample, and a parameter is a descriptor of a population. So sample means were just a statistic, okay? It was a number meant to summarize data after it had been collected. This lesson, we're going to learn how a sample mean, as well as others, but we'll get to that in a minute, can also be a random variable, okay? So we've learned about random variables. Now we're going to take a sample mean and turn it into a random variable. A sampling distribution for the sample mean would describe the means of all possible samples of a particular sample size from a specified population. Okay, that's a little overwhelming, but I have an example in just a minute that's going to help with that. Since the value of the sample mean for any particular sample depends on the sample we draw, the sample can now become a random variable. So I want you to think about this. We have a population. I don't know what the population is, right? But you need to figure out the mean, right? Now, the mean that you find literally depends on the sample that you pick. Like if I were to talk about this class and I were to choose the front two rows as a sample and I were to find their average height, that might be very different than if I were to come to the back two rows and find the sample mean for their average height. The sample means can vary. It's very strange. So like it's all dependent on the sample that you choose to see what value you get back. Does that make sense? So since it depends on the sample we draw, that's what makes it a random variable. The best way to summarize outcomes of some random phenomena is with probability distribution. The probability distribution, which describes the distribution of the sample means, is called, and I need a pin for this, the sampling distribution of the sample means. So here's what that's saying. That's saying I can take every single possible sample. So let's say I choose a sample size. In this class, we have about 25 people. I want my sample size to be 5, okay? So I'm figuring out how many samples of 5 could I make. And then I find literally the sample mean of every single one of those samples. Okay, so I take the first 5 people, make it a sample, and then find the mean. And then like I take the next sample of 5, and 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 there's like so many of them, right? And I find every single possible mean I can, and I can create a sampling distribution. And that's what this guy is down here. They made it into a histogram. They found all the possible sample means, and they made it into a distribution, okay? So a sampling distribution is a statistic that is arrived through repeated sampling from a larger population. It describes the range of possible outcomes of a statistic, okay? That's just what I explained. So let's talk about this example, and it's going to help you understand. A regular can of Coke is labeled to indicate that it contains 12 ounces. Like we have grown to know and trust this, whatever. We could not go through and physically check each and every can that comes through the line because it would destroy the product. Does that make sense? Like they're not going to open every single can of Coke and triple check that it's 12 ounces. That would then they would have nothing left to sell. So instead, they sample. So here, we know that the population mean of a can of Coke is 12 ounces. Like that's what they label it as. So I'm going to just say we're going to choose a sample of 48 cans. Okay? So on the distribution line, we have all these cans of Coke. We're going to choose a sample of 48 cans, and we are going to measure how much is actually in them, and we're going to find the sample mean. So the first sample of 48 cans that I choose has a sample mean of 12.19 ounces, so a little more, right? Then I'm going to do it again. I'm going to go back to the distribution line. I'm going to choose 48 more cans, and I'm going to find the sample mean. That time I got 12.23 ounces. Then I'm going to do it again. I go back to the distribution line, get 48 new cans, and this time I get a mean of 11.98 ounces. Does that make sense? You can do this over and over and over and over. We can do this as many times as we want to get accurate data. Okay? The more times we do it, the more accurate our data is going to get. Now, if you are finding the mean amount, you would expect that some of these sample means would be above 12 ounces and some of them would be below 12 ounces, right? Because when you average them together, we want 12 ounces. So that's what we're talking about. We're finding multiple sample sets and we're finding the means of all of them. Okay, since finding the population parameters is often impractical, like we just discussed, the best alternative is to use sample statistics. That means that if you are wanting to estimate a population value, the corresponding sample value would be a good estimator. We already know this. A point estimator, this is a new vocab word, a point estimator is a single valued estimate calculated from the sample data, which is intended to close the true population value. So, sample mean is the point estimator for population mean. Sample standard deviation and variation are the point estimators for population variation and standard deviation. And then sample probability is the point estimator for the population probability, right? Basic information. Sometimes the sample mean may be off from the population mean based on the sample that you chose. We already discussed that with the height. It depends on the sample that you choose. That's why it's important to understand how the sample mean varies and thus reduce the probable error. Okay, so we're going to do this example and I'm going to help you come to the conclusion that this makes sense. Suppose that the quality control department wished to determine the average diameter of a shipment of valves that are used in the manufacture of respirators. Clearly, we cannot measure every single valve as it would waste too much time. So the quality control group has decided to select 2 from a batch of 6. So here's what's going on, okay? A quality control department gets a shipment of 6 valves. We're just going to name these 6 valves A, B, C, D, E, and F, okay? We officially do not know the measurement of these valves, but I'm giving you the measurement so we can see how this works, okay? So when they get these valves, they do not measure them. They do not know the measure. They could technically measure each of the 6, but like we're just choosing 6 to make it easy. What if it was a shipment of 100? We're not going to go through and measure 100 diameters, okay? So we get these 6 valves. From this population, I want you to go ahead and find the mean and standard deviation. Notice it does specify from this population. They're saying these 6 valves are the population. So let's come here, and we're going to find the mean, so average of these 6 valves. And then we're also going to find the standard deviation of this population of these 6 valves. Now I'm going to change these to 4 decimal points because that's what usually Hawks asks for, okay? So this data right here, this quality control department does not know this, okay? They do not know this. They only have the 6 valves. We are saying, hey, we know this data, we're going to see if it checks out, okay? So the average diameter of this population is 0.1483 with a standard deviation of 0.0246, okay? Again, the diameters are not known by the quality control group when the shipment arrives. Now, they're saying they're going to take a sample of size 2. Now, if I have 6 valves, how many different samples of size 2 can I make? Just a reminder to figure this out, you would do combination, C-O-M-B-I-N, of 6, choose 2. So how many different sample sizes can I make? We can make 15 different samples. If we have 6 valves and we only want to choose 2, there are 15 different possibilities of the groups that we can make. Now what I've done is I've actually made a table here of all the different possible groupings we could make. They could choose valve A and B, A and C, A and D, A and E, A and F, B and C. You get what I'm saying? I listed them all out for you. So here's what we're going to do. We are going to find the sample mean of each one of these groupings. Now, there's 15 of them. I'm not going to make you find the sample mean of each one of them. I'm going to break it up. So here's what I'm going to do. I'm going to number you off, and you're going to find that sample mean, and we're going to come back, and we are going to compile our results. So those of you in video land, I'm going to pause the recording, and then we're going to come back and have all the sample means. Okay, so those of you watching this video, you can go ahead and pause the video and copy down all of these sample means. What I just explained to the class is that we found every possible sample of a group of 6 that we chose sample size 2 possible, and we found all of their means, okay? Now what we're going to do is we're going to come down here, and it says, what is the mean of the sample means? It's saying, okay, you have this whole list of all of these sample means. Can you find the average of that? So I'm going to come over here, and I'm going to type in equals average of, and I want to select all of those sample means, those 15 sample means that we just found. So I want to find the average of all of those, and I want that to be to 4 decimals, and guys, what do we get? 0.1483. And if you'll notice, 0.1483 is the population mean. Do you guys remember that? Those are the exact same. So when I found every single sample mean that I could and I averaged them together, I got the population mean. When that happens, that means this is unbiased. This is an unbiased measurement, okay? Unbiased. That's really awesome when it happens. That's what we want to happen, okay? So since the average value of the estimator is equal to the population parameter being estimated, the estimator is said to be unbiased. Now, we do have estimators that we know are unbiased. The sample mean is an unbiased estimator of the population mean. That's going to happen every time. The sample proportion is an unbiased estimator of the population proportion. The sample variance is an unbiased estimator of the population variance. That's how it works. Things that are not unbiased would be like range. Okay? The sample range is not going to be an unbiased estimator of the population range. They're not going to be the same. Okay? Estimators are similar to marksmen. When you shoot, you want to hit what you're shooting at. When you estimate, you want to get as close as possible to the population characteristic that you're estimating. So I have a nice visual here, and we have 4 targets, okay? Target 1 and target 2 are really good examples of unbiased estimators. So target 1, we have a lot of variability, but it's all centered. If I were to take the average of all of those, it would be the bullseye. Does that make sense? Which is the population parameter, okay? Target 2, we still have variability, and if I were to take the average of those, I would still get the bullseye. That would be unbiased. Target 3 and target 4 are examples of biased estimators. So target 3, if I were to take the average of those, they're all kind of grouped together. So like if you were to get a sample, they were all grouped together like that, you would get an average of like somewhere in here, which is not the population parameter, okay? Target 4, these are a lot closer, and probably the average would be a lot closer, but there's not a lot of variability there. Those are biased. So if an estimator is unbiased, its variability determines its reliability. If an unbiased estimator is extremely variable, then the individual estimates it produces may not be close to the parameter being estimated as estimates produced by a biased estimator. So here's what that means. If an unbiased estimator is extremely variable, that would be like target number 1, okay? Target number 1 is extremely variable. They're all over the place. The individual estimates that it produces, meaning each individual little black dot there, might not be as close to the parameter as if we were talking about target number 4 here. Target number 4 is biased, but each one of those individual estimates is closer to the population parameter, okay? The variability of an estimator reveals a great deal about the quality of that estimator. In order to assess how well the sample mean estimates the population mean, the variance of the sample means must be determined. So what we're saying is, how do we know if we have a sample and we take the average of it, if that's a good estimator or not? Like, how do we know? That's all dependent on the variability, okay? Now, the variability would be the variance in the standard deviation. So we are going to have to talk about how to find the variance and standard deviation of the sample mean. Now, there's 2 different methods here. There's an infinite population and a finite population. So like the cans of Coke, that would be an infinite population. It's a very large one. But a finite population would be like the diameters of the valve. There was only 6. Does that make sense? So it can be shown that for a population of infinite size, the variance of x bar, and it's written like this, and so some people think it looks like variance or standard deviation of 2 over x bar. No, what that really means is variance, so sigma squared, sub x bar. That's what it really is. So the variance of x bar equals the the population variance divided by your sample size. Okay, so to find the variance of your x bar, you need to take the population variance and divide it by your sample size. The standard deviation is just the square root of that. Okay. Now, when you're dealing with a finite population, it's the same concept, except we have to add this bad boy right here into it. Now, when it's a finite population, we know the size of the population, we know the size of the sample, so we have to multiply our variance by the population size minus the sample size over the population size minus 1. They just add that in there. Okay? As the sample size increases, the variability of the sample decreases. Here's what that means. As our as our sample gets bigger and bigger and bigger, our variability is going to get smaller and smaller and smaller, meaning the bigger the sample size, the more accurate measurements we're going to get, which makes sense. The bigger the sample size, the better readings you're going to get. It just all depends on like what you're dealing with. Sometimes we can't have a big sample size, like the cans of Coke, because we're going to lose all our product. So let's talk about some characteristics of the sample mean. There are 2 characteristics of the sample mean here that we just discussed, okay? First thing, if an estimate of the population mean is required, the sample mean seems to possess 2 good characteristics. The first one, the mean of the sample means is the population mean. Another way of expressing this concept is to say that the expected value of x bar is equal to the population mean. We just proved that with those valves. We found all the sample means, we found the average of them, and it turned into the population mean. Also, if the sample size is increased, the variability of the sample mean decreases. This implies that the quality of the estimator tends to improve, the sample size increases. That's what we just talked about. The bigger the sample size, the better. Okay? Now, that leads me to the central limit theorem. Okay? The distribution of the sample mean becomes closer to a normal distribution as the sample size becomes larger. The bigger the sample size, the closer to a normal distribution it's going to be, regardless of the shape of the population from which the sample was drawn. Your population could be whatever you want. It could be distributed however it wants. But the bigger the sample size you get, the closer to a normal distribution it's going to be. So, if a sufficiently large random sample, this is important, a sufficiently large random sample, that means if you have a sample that is greater than 30, okay, if you have a sample that is greater than 30, drawn from a population with mean mu and standard deviation of sigma, the distribution of the sample mean will have the following characteristics. So if my sample size is larger than 30, the first thing we need to know is the distribution of the sample means will be approximately normal. Okay? If your sample size is larger than 30, the distribution of the sample means will be approximately normal, so it should be bell-shaped. Okay? The second thing is that the mean of the sample means is going to equal to the population means, like we did with the valves. And the third thing is the standard deviation of the sample means equals the standard deviation of the population divided by the square root of the sample size. So let's work some examples like you're going to see on your homework. Read carefully for details in the problems, as they're going to have key phrases such as less than, more than, differs by less than, and differs by more than. We've seen these phrases before, so read carefully for those. So when we're dealing with means, there's an Excel function that we're going to use, and that is norm.dist. Okay, norm.dist. Okay, that is normal distribution. But this is not a normal standard distribution. So when you're typing it in, you're going to have norm dot, and there's going to be options that come up, norm.dist or norm.s.dist. This is not a standard distribution. This is sample mean, so it's just norm.dist. And into that formula, you're going to put 4 things. First of all, we're going to put our sample mean, which is x bar. Then we're going to follow it up with the population mean, which is mu. Then we're going to have the standard deviation of the mean, so sigma sub x bar. And then finally we put true. Now, this formula right here always gives me the area to the left. Okay? It always gives me the area to the left, so keep that in mind when we're working these problems. So the first problem we're going to work with on number 1 is a less than problem. It's a less than problem. So it says, if a sample of size 40 is drawn from a population that has a mean of 276 and a variance of 81, what is the probability that the mean of the sample will be less than 273? So what we've got to do is we've got to take all of this information that they gave me in this problem, and we've got to put it into this formula. So we're going to have to organize a little bit. So first thing is they said a sample of size 40. That means my n value is going to be 40 here. Sample of size 40. And it's drawn from a population that has a mean of 276. That means my mu is going to be 276. Okay? And a variance of 81. Now variance, remember, is sigma squared, and they're saying variance of 81 after following that population. So that's a population variance of 81. And can you guys tell me, what does that mean my population standard deviation is going to be? Just 9, because it's the square root of it. Okay? They're asking, what is the probability that the mean of the sample, so that would be x bar, is going to be less than 273? Okay? What is the probability that the sample mean is going to be less than 273? So what I'm going to do now is I'm going to sketch a picture of what this is going to look like. So we're going to have our normal distribution, okay, because our sample size is larger than 30, so it's going to be a normal distribution. And it says the mean is 276. They want to know what is the probability that whatever we choose is going to be less than 273. So 273 is over here, and it's going to be to the left of it. Okay, what's the probability that it's going to be less than 273? So when it's less than, it's very straightforward for the Excel function that you're going to use. You're just going to come over here and you're going to type in equals norm.dist, and from there we have to put in the information that they gave me. So the first thing we need to put in is the sample mean. What sample mean are they asking us about? What is the probability that the sample mean will be less than what? 273, very good. Comma, the next one they want is your population mean. What did they say my population mean was? 276. Comma, the next thing we need is the standard deviation of the means. You have to be careful here. The standard deviation of the means is not the same thing as the standard deviation that they gave me. Notice, this is just sigma. They want sigma sub x bar. So this is where things are a little bit different. Now, if you'll remember back up here on the practice, sigma sub x bar is given right here. We find the standard deviation of the means by taking the actual population standard deviation and dividing it by the square root of the sample size, right? So here's what's nice about this. I can do that calculation right in here. I can take the the population standard deviation, which we said was 9, and I can divide that by the square root of the sample size. What did we say my sample size was? 40. So you cannot just put in the number 9 there. You have to do a little calculating. And then finally you can put true. Okay? And then again, Hawks is probably going to say round to the nearest 4 decimals, so we would want 0.0175. So the probability that the mean of your sample that you choose is going to be less than 273 is 0.0175. Now, that was a lot to do in one function. Here's what else you could do. You could start by saying, okay, I know that I need to find the standard deviation of the means. And to do that, you could literally come over here and say, okay, that means I have to take this population standard deviation and divide it by the square root of the sample size. So you could work that out right there. And then when you do your norm.dist, you could type in 273, 276, and then you could do a cell reference so you don't feel like it's too much in one, and it'll get you the same thing. Okay? All right, let's look at number 2. Number 2 is a greater than problem. So it says, suppose a population has a mean of 30 and a variance of 25. If a sample of 100 is drawn from the population, what is the probability that the sample mean will be larger than 31? So let's take this information and jot it down quick. First of all, it says a population has a mean of 30. So would that be what symbol? Do we remember? Mu would be 30. And a variance of 25. So what would my standard deviation be, or sigma? 5, good. If a sample, which is n, of 100 is drawn from a population, what is the probability that the sample mean, so x bar, is going to be greater than 31? Okay? So what I did on this one is I typed it instead of writing it, because I know that you guys don't have like a stylus like I do. So if you're taking notes on your Excel document, this is how you can do it. Now, if you put variance, you could also put sigma squared, or you could put population variance, so you remember, okay? So those are ways that you can take that information and put it into Excel without writing. Now, I always recommend you have notebook paper to sketch out on your problems on homework, because like to have a visual seriously helps a ton here. So we know that it's going to be normally distributed because my sample size is larger than 30. The mean of this distribution, we said, was 30. But it says, what is the probability that the sample mean is going to be greater than 31? So here's 31. I want to know, what's the probability that the sample that we choose has a mean that's greater than 31? Now you have to be careful, because the norm.dist function that we've been using gives me the area to the left. Okay, so how am I going to do this to find the area to the right? Do you remember? 1 minus, good. So here's what I'm going to do first. I'm going to start by finding the standard deviation of the means. So the standard deviation of the means. Again, you can do this actually in your norm.dist, but I just like to keep things separate so I don't get confused. Now to find the standard deviation of the means, according to our notes, is we take the population standard deviation, or sigma, and divide it by the square root of our population size. Sigma divided by radical n. So this is going to equal sigma, which now since I typed it in, I can do a cell reference, which is nice, divided by the square root of my n value. Now some people are like, Mrs. Guess, I know that the square root of my 100 is going to be 10. Can I just type that in? Yes. But like if it's not a nice number, that's why we have the square root function. So the standard deviation of your means should be 0.5. Now let's use that to find the answer. So you said 1 minus, which is perfect, norm.dist of the x value is the sample mean. What sample mean did they want? 31, comma, what's my population mean? 30, comma, my standard deviation. Now, I always do a cell reference. So some people look at that and they're like, it's just 0.5. We don't really know that unless we like expand the decimals. Maybe it's 0.512. I don't know. So just do a cell reference if you do that. Never cut it off. And then finally put true. And we get 0.0228. 0.0228. So the probability that the sample mean is going to be larger than 31 is only 0.0228. All right. Number 3. This one is a differs by less than. A differs by less than. The operation manager at a tire manufacturing company believes that the mean mileage of a tire is 23,383 miles with a variance of 21,436,900. What is the probability that the sample mean would differ from the population mean by less than 533 miles in a sample of 286 tires if the manager is correct? So the things that we have to find here, we have to find the sample size, we have to find the population mean, we have to find the population variance and standard deviation, okay, and then we also need to find the probability that X bar differs by less than 533. So here's what I want you to do. I'm going to pause for a second. I want you guys to find your n, mu, sigma squared, and sigma for me. M, mu, sigma squared, and sigma. So help me out. What is my n value? 286. Very good. What is my mu value? 23,383. What is my variance? 6,900. And my standard deviation, I'm just going to go square root of that bad boy. And, oh, it's a nice number, which is a good feeling. So 4630, right? Now let's get a visual of what they're asking here. Again, we know it's going to be a normal distribution because the n is greater than 30. Okay. Now my mean, we said, was 23,383. Okay. What is the probability that X bar differs by less than 533? So that means I'm going to go 533 this way, and I'm going to go 533 this way. Okay? So what is the probability that it differs by less than that? So to figure out what these numbers are, we're going to have to take 23,383 and add 533, and that's going to give me 23,916. And then I'm going to have to take that and subtract it, which is going to give me 23,856. Okay? So I want to know what's the probability that my sample mean is in that range. Are we okay with that? Can you remember how we did that? How did we find it in between those two? Good. We have to take the bigger one, so we're going to have to do norm.s.dist, or excuse me, norm.dist of the bigger one here, yes? And that's going to give me all of that yellow area. And we're going to have to subtract norm.dist of the smaller one, which is going to give me that blue area, and that's going to leave me with whatever was in between. So first thing we're going to do here is we are going to find sigma sub x bar. Okay, so we're going to find the standard deviation of the mean. So standard deviation of the means. And again, that equals your population standard deviation divided by the square root of your sample size. And you should get 273.7 repeating, or 7776. That wouldn't be 7 repeating. Goodness. Okay. All right. Let's figure this out. So we're going to start with norm.dist of, and we're going to start with the bigger one. So the bigger one we said was 23,916, comma the mean, 23,383, comma my standard deviation, which we just found, so that would be a cell reference, comma true. $23,916. This guy right here, my mean plus 533. Keaton, you can also do this. You can also come in here and say 23,383 plus 533. That would work. The reason for that is because it says differs by less than 533. So if I go 533 to the right and 533 to the left, I want it to be in that range. Okay? Then we're going to go minus norm.dist, and we're doing the smaller one now. So 23,853, comma 23,383, comma standard deviation, comma true. Ah! No, I wrote it wrong. It should be 22,856. What did I write? Oh my goodness. Hold on, let's find out. So we're going to do equals 23,383 minus 533. 22,850. Like, what did I write? Oh no, I did write that. This should be 22,850. So when I go in here, my norm.dist, that should be 22,850. Clearly, I was not in the right line there. Oh, I was looking at the wrong problem. Oh, that'll do it. Okay. Okay, let's try the last one here. The last one is differs by more than. So the mean per capita consumption of milk per year is 132 liters with a standard deviation of 25. If a sample of 196 people is randomly selected, what is the probability that the sample mean would differ from the true mean by more than 5.15 liters? So again, we need to find my n value, we need to find my mu value, and this one is a little different. They didn't give me a variance, so I don't have to list the variance because I only use the variance to find the standard deviation. So since they gave me the standard deviation on this one, that's all that I have to list. And here I want the probability that x bar is going to differ by more than 5.15. So take a second, find those three values. So what's my n value? 196, that's my sample size. What's my population mean? 132. What's my standard deviation? 25. Okay, so let's go with a visual of this. Again, my population is bigger than 30, so it's going to be normally distributed. Okay, it's going to be normally distributed. My mean is that 132. They want to know what is the probability that the sample mean would differ from the true mean by more than 5.15 liters. So I'm going to go 5.15 this way and 5.15 this way. Okay? So I'm going to go 5.15 and 5.15. So to get this value, I'm going to take 132 plus 5.15. So that's 137.15. Okay? To get this number, I'm going to take that 132 minus 5.15. Okay, so that's going to give me 126.85. Those are my two values. But we want to find the probability that it differs by more than. So I want this shaded area outside of it this time. Okay? So to get this shaded area right here, I'm going to highlight. To get this shaded area right here, do I have to do anything special? No. This one is going to be the regular norm.dist. Okay? But what about to get this yellow shaded region here. Do I have to do anything special to get that yellow shaded region? Yes, here I have to do 1 minus norm.dist. Okay? Then what do I do with those results? We're going to add them together. So first thing I'm going to do is I'm going to come over here and I'm going to find the standard deviation of the means. And to do that, we take the standard deviation divided by the square root of the population size. Now, you can do this all together in one cell if you would like, but personally, I feel like that leaves me too much room for error. So I'm going to do two different ones. I'm going to do the left side and I'm going to do the right side. Okay? So to do the left side, we notated in our notes that it's just norm.dist. Okay, it's just norm.dist. So that's 126.85, 132, standard deviation, and true. So 126.85, comma 132, comma standard deviation of the mean, so that's a cell reference, comma true. 1.78, 1.785. That's that formula that we have up in the notes. So the standard deviation divided by the square root of the sample size. Okay? Now let's get the right side. The right side is going to equal 1 minus norm.dist. My x value is going to be 137.15. My mean is 132. My standard deviation is the cell reference, comma true. Okay? Then to get your total value here, your total value, you're just going to add those two together. To get your total value, just add those two together. Now, tell me something. What do you notice about the answer you got for the left and the right? They're the same. Why is that? We have that line of symmetry. That mean is the line of symmetry. So if I'm moving 5.15 to the right and 5.15 to the left, the area on the outside is going to be the exact same on each side. So instead of doing the left and the right, the other way you could do is just find the area to the left, and then to get your total answer, you can just multiply it by 2. Oh. So equals this times 2. And it'll get you the same thing.